In this last video of the chapter, we are going to see an application of these invertible sheaves that we have studied in the last videos to an actual very classical question that we could have asked a long time ago, namely the question of how to determine maps to projective space. And so for this, let's start with recalling some important things. So on the projective space Pn, we had these twisting sheaves. And we saw that they are invertible sheaves or associated to line bundles on projective space. And we know about their sections, the set of global sections of OPN of D, when D is non-negative, is just the degree D part of this polynomial ring in n+1 variables, which is the same thing as this homogeneous coordinate ring of Pn. And in particular, if we take d equals to 1, then we just get the homogeneous linear elements here. So in other words, just the linear span of x0 up to xn. And on the other hand, we did study maps to projective space already. And we saw that if you have another projective space, for example, and you have n+1 elements of this homogeneous coordinates ring of the same degree, d, then you get a morphism, which is defined kind of almost everywhere on Pm. You have to throw out the common vanishing set of these sections. And this map to Pn is then just given in homogeneous coordinates by these f0 up to fm. And now, with the thing that we called here, we can interpret these f0 up to fn as elements of the space of sections of the same line bundle, namely this line bundle L, which is OD on this Pm. So we get a morphism of 2Pn, basically specified by these n+1 sections of the same line bundle. And the idea is this is not a coincidence in this case, but this is a general theorem. And so this is the following: given the variety x over k, there is a bijection between the morphisms from X to the projective space Pn and the set of such tuples of L, which is an invertible sheaf, so a locally free sheaf of rank 1 over X. And then these S0 up to Sn, these are sections, global sections of L on X, which have the property that for all points in X, there is at least one element I, one index, such that the ith section doesn't vanish at this point. So we again see this property, they shouldn't all vanish at the same time. And you take such things up to isomorphism, which we're going to see in a second. But the basic idea, how you start from left and go to right, is you take such a morphism, F, and then the line bundle that you obtain is just you pull back the line bundle O of 1. This lives on Pn, and you pull it back under F, and then you get this line bundle L on X. And to get the sections, well, this O of 1, as we have seen here, this has n+1 sections, namely just associated to the coordinates x0 up to xn. And if you pull back these sections, then we have seen you get a section of the pullback line bundle. So these S0 up to Sn, these are now sections of this L. So this is the association, how you go from left to right. In the proof, we're going to see how you go back. And just to say, what do we mean by isomorphism here? Well, two such pairs are isomorphic if there exists actually an isomorphism of these sheaves, sending the Si to the Si prime. That's the full statement. So this shows you that understanding morphisms to projective space is very much related to understanding line bundles on your space and the sections of these line bundles. Okay. And so before we start, I wanted to show a small lemma that we're going to use in the proof. And this tells you something about automorphisms of this line bundle, of the trivial line bundle OY. So if Y is a scheme and you have an isomorphism from OY to itself, then this can basically be uniquely determined by knowing what does this isomorphism do on the regular function 1, right? I mean, 1 is always a section here, and this gets transported to some function s like this, and the claim is this function s is an invertible function, so it's nowhere 0 on y, and then it uniquely determines this psi because psi of some function phi is just s times phi. It's just multiplication by this s. And the proof is not so difficult. So somehow let's assume, so let's try to first compute actually the second part. So let's try to compute what is psi of phi of such a function. Well, we can write it as phi times 1. And then, because this is a morphism of OY modules, it is linear under pulling out multiplication by a function in OY, like phi. So somehow we can just pull out phi like this. And then by definition, this psi of 1 is just s. So somehow this part, this kind of second part here, basically automatic. It's just a statement that psi is an OY module homomorphism. So let's also write this down. And then to show, the only thing that remains to show is that this S is invertible, but there we need to use that this is an isomorphism. So somehow if we call then T to be just the image of the inverse of this, of 1 under the inverse map, then, well, it's true that 1 equals psi of psi inverse of 1, of course. And then we apply the same reasoning that we had here to psi inverse, and then we see psi inverse of 1, well, this is T, and then psi applied to this is just S times T. We get S times T. But then we see 1 is equal to S times T. This implies that S can not vanish at any point. So in other words, S in OY, I mean, you can either write it like this, or you can say somehow in the set of global, I guess here, this is the set of all functions, and this is actually an invertible element. Like this finishes the proof. So this tells us something about automorphisms of OY, and this will be useful in a second in the proof. Okay, so the first thing that we want to show here, now we go to the proof of the theorem. The first thing we want to show here is that this here is a well-defined element here. And for this, we just recall some of the properties of pullback. So first of all, we want to show that L is an invertible sheaf. But we know that OPN1 is locally free of rank 1. And then we have seen, if we pull this back under a morphism, then it's still locally free of rank 1. So it is an invertible sheaf. And then the xi are sections of this line bundle before pulling back, global sections. And so the Si, which are defined to be the pullbacks of these, are sections of the pullback line bundle on the pre-image of Pn, but the pre-image of Pn is everything, so there are sections on X. So we have already shown this is an invertible sheaf, these are sections, and now we need to show this last property that they don't all vanish at the same time. And this comes, of course, from the fact that in Pn, not all the coordinates are allowed to vanish at the same time. And so to make this precise, let's assume we had this Si of P was 0 in this fiber of L at P. which is the same thing. So the fiber of the pullback line bundle at a point is the same as the fiber of the original line bundle at the target point, right? So somehow this vanishing here is equivalent to saying that, so under this isomorphism, this Si goes to the Xi. So in other words, the Xi at f of p vanishes. So here we use that this is the pullback here. And then this goes through this this isomorphism. And there's one thing to check here, which we're not going to do, namely that this vanishing, I mean, this looks very suggestive, right? This says the coordinate function xi at this point here vanishes, and you can check this is indeed exactly what it says. This is equivalent to saying that this is in the vanishing locus of xi. So somehow here this xi is an abstract section of this, and this xi is now this vanishing of xi is the usual thing that we defined, just the set of points whose i's coordinate is 0. And making sure that these definitions fit together. So this vanishing is equivalent to this, but we know that the vanishing locus of all of these together is the empty set. And so not all of these Si of P can be 0. Okay, so this shows this is a well-defined map in one direction. And so to prove that that there is indeed such an bijection, we just have to go from this right-hand side to the left-hand side. So we give this as input data and try to get out such a morphism to Pn. So let's assume we have given such a tuple as above. Now we need to construct maps to projective space. And so since L is locally free of rank 1, it follows that we can find a trivialization. So somehow on some cover that we can find, on some such cover of X, so depicted here, these things are actually trivial. So somehow L restricted to UI is by some map phi I isomorphic to O UI. And then all these sections that we have, the Sj, by the same isomorphism, by the phi I, go to some functions fj ui. These are just some functions now. So sections of this thing here, so we get regular functions. Okay, so now we have n+1 regular functions, and so we get from this a map. This fi, which is just given in these homogeneous coordinates as f0 ui and fn ui. This goes from ui to Pn. This is a well-defined morphism. So we have already seen back in the days that if you have n+1 regular functions, then this defines a map to Pn. So we have used several times. And this is well-defined because for all p, there exists a j such that fj ui of p not equal to 0. Okay, so we do get things on this open cover, and now we just have to check that these glue together to a nice function to Pn. So they agree on the overlaps. So on the overlaps ui intersect uk, well, we have that this we have kind of two possible ways. If we start with the L restricted to UI intersected UK. And we can once trivialize it by this map phi I, and once we can trivialize it by the map phi K. And if we compose these two trivializations, these two isomorphisms, then we get an isomorphism phi ik. And now here we see why the lemma was useful that we proved, because the lemma tells us such an isomorphism from the trivial line bundle to itself is given by multiplication with a function. So the lemma shows that the phi ik given by multiplication with sik, which is a function on UI intersected UK, and this function is actually invertible. Okay. And then now we just compare the two maps which we constructed. So the fi on the UI intersected UK is given by, well, this stuff here. Just copy paste. I guess this was not faster than writing it again. Okay. And so these things are now, by definition, if we translate them here, they're just given by multiplying with the same function in all the coordinates. So this is sik times f0 uk to sik times fn uk, like this. But I mean, somehow Pn is invariant under scaling. That's basically the defining thing. And so, in fact, we can kind of remove all these common factors again, and then just get f1 uk to fn uk, which is just the definition of fk. And similarly, so somehow these things agree on the overlaps, and so they glue together. So they glue to map f from x to Pn. And similar, so if you recall, there was this notion of isomorphism. So if we have isomorphic collection of data here, then all these functions f, j, u, I prime cooked up from this differ from the f, j, u, I without a prime by a common vector si. So having isomorphic data means that you have an isomorphism from L prime to itself, and then you can check that this is again given by multiplication by a certain constant here. Or sorry, not a constant, but a nowhere zero function. And so this gives the same map to Pn. Here, the place where we kind of used, so this is not so important, but I mean, the place where we use that X is a variety here is just that morphisms from this variety to this variety, if checking that they agree, for example, agree on these overlaps, this can be done just by checking what they do on points. So this made our life a bit easier here. But in fact, the theorem holds more generally. So what we have done is we have shown the map from left to right is well defined. We have given a map in the other direction, and then a slightly tedious exercise, which we're not going to do, is to check that these two constructions are actually inverse. So they are given by bijection. If you want the details, These are in Bakir's notes, for example, in section 15.2. Okay, so this is the proof of the theorem. And then this can be applied for studying very classical questions like maps to projective space. In particular, the following kind of small application that we might also see in one of the exercise sheets in the last week is there's a theorem which actually tells you that every line bundle L on projective space is just of the form L is one of the twisting sheets. So we have fully understood what all the line bundles there can do. And then this can be applied to the question of what are the maps from projective space to itself. In particular, what are the isomorphisms from projective space to itself? Because they must be given by the choice of a line bundle and these n+1 sections. And this can be used to prove that the automorphism group of Pn over some field is just these projective general linear groups of n+1 cross n+1 matrices invertible up to scaling. So this is a statement which we had seen a long time ago, and we had kind of skipped the proof. One reason is that in order to prove it, one very nice way is to use this theory of invertible sheets. Okay, this was everything about the quasi-coherent sheaves, showing at least in this last video some small application. And in the last chapter, we're going to talk about some particularly geometrically meaningful quasi-coherent sheaves, which are the sheaves of differentials on a variety and how they can be used to characterize when the variety is smooth.